Let's start off with Lewis, acids and bases. Okay, so this is chapter 15. A Lewis acid is an electron pair acceptor, and a Lewis base is electron pair donor. So a Lewis base is either going to be something that's negative, with a negative charge, or you see a bunch of extra lone pairs on it. A Lewis acid, you either do not see lone pairs on it, and or it has a positive charge. So, I think somebody just asked me this one, so it's fresh in my mind. Okay, we're going to identify the Lewis acid and the Lewis base. So the first thing now, that hopefully you know when you look at reactions, is to find out, is there any spectator ions? So I would always think about that when you approach any problem, because when there's a spectator ion, you just cancel it out or ignore it. And so K, in both cases, I'm going to ignore because it's a spectator ion. It's a conjugate of a strong potassium hydroxide. And so it's neutral. So really we have I minus and I3 minus. So with very little thought involved, now I see the minus, so I'm thinking it's a base. And thus by default the other one's an acid. Okay, now these will both have lone pairs on them if you do have the Lewis structure, so that really won't help you in this case. You're just going to have to go by the negative charge, and this has more negative, so it's going to be the base. It's an electron pair donor. It has more negative to give. Okay, cool. So make sure you can identify those. They're still acids and bases just like before, but you'll see here there's no protons involved, and so the Lewis definition is most helpful. Next, let's do acid, base, or neutral. Yeah? That's a good point. So why isn't I a spectator ion? Generally you would think it is because it's the conjugate of HI. However, in this case, you find that you make an I3 complex. You know that's not neutral. You know that I2 is not a neutral or spectator ion. And so this must have been involved in reaction in this case. The K, I didn't think that because it just carried straight as is across. So you do want to, that's good, we'll put the caveat on there. If you see it reacting to make a new chemical, sometimes that will happen with spectators, or what we think is a spectator, then you can't cancel out, and you can see there's no way to cancel out an I minus here because there isn't even one. If there was an I minus on the right hand side, we would cancel it. Good. Okay, next, let's do acid, base, or neutral. Oh, and then remember one more thing to add on to what you just asked me. For example, water is neutral, but it can still be an acid or a base. So we can have what is neutral compounds, which we would classify that one as, still acting as acid or base. Okay, good. Okay, for acid, base, or neutral, let's just try a couple examples to make sure we're kind of savvy with this. So let's take a look at the periodic table. I want to do, no, not that one, that's too crazy. NH4Cl, no, NH4Br, sorry, it took me a while. Okay, so you don't have to do it so explicitly as we've done it in class if you're kind of getting used to doing this, but to do it more explicitly, you write out the ions, and then you write out the conjugates. And here you could write, for NH4+, you can write NH3 or NH4OH. It won't matter. And then I'll get a different color pen. You're going to identify HBr is strong acid, so we got a neutral here. And then NH3 or NH4OH, it's a regular base. So this is a regular acid, and acid plus a neutral, we've got an acid here. Okay, let's try one more example. So you just want to follow this flow anytime you do a problem. Let's see. Let's try this one, see if it works out. Okay, we've got sodium and PO4 3 minus. The sodium is from NaOH. The PO4 is from H, PO4 2 minus. Okay, get my other color pen out. The sodium hydroxide, that is a strong base. So sodium, we should know, is one of our spectator ions, or it's neutral. Here, we've just got a regular acid, so this is a regular base. And thus, this would be basic. Okay, any questions on either of those two before we move on?
Question?
Yeah.
What do you do if you have like a really long, like if there's like multiple like elements put together? Because like you have
Like this has multiple elements together.
more than that though. Like there's one in your reader, it's like C2H5 and H2. Yeah.
Like that?
Yeah.
Okay. This is, okay, let me write this. You've seen ammonia before. All ammonia is 3 H's. But any of these 3 H's can substitute for any organic compound. So C2H5 is substituting for one of the 3 H's. And you have 2 of the H's left. You can see it right there. So ammonia, a nitrogen compound as neutral, like ammonia, will have 3 things on it. They can either be a hydrogen or an organic. In this case, this is equivalent. You should think, oh, this is basically like ammonia. So there's nothing to do with it except to call it a base, because ammonia is a base. Okay, so you don't really have to do any of this. All of this process that we go through is for ionic compounds. Right here we don't have this is just a molecular compound. So if you see an N, and it's neutral and there's 3 things on it, just think of it like ammonia. If you see an N with 4 things on it, it should have a plus charge, and you would think of it like this, NH4 plus, and that would be an acid. Is that all right?
Yeah, thank you.
Yep. So you'll see a lot of those kinds of ammonia compounds around. Don't let them throw you. Okay, let's do relative acidity and basicity. All right, so if I give you any set of compounds, you should be able to tell me which one, what's stronger or what's weaker. Okay, so if you saw these 2 compounds, you're always looking, and there's really 3 differences you're looking for. One possible difference is this one here, where it's one element substitute for another, or oxygen for a sulfur. In that case, it's a periodic table sort of problem. You want to find the one that is more to the right and down, and that would be sulfur. Sulfur is below oxygen, so the one with the sulfur will be the stronger acid. Okay, to answer the question of somebody over there about which one's the stronger base, it would have to be written in base form. In base form, it would look something like this. I'll put just a spectator ion K on there. Oops, that was it. S. I'll put a K just for a fun spectator ion. And then you would think, well, if this one was the stronger acid, is that okay? Then the opposite one has to be the stronger base. That's it. So once you know one set, you know what's a stronger base. It's just the opposite of what you got for the acid answer. Yeah? Does electronegativity matter? Electronegativity is overcome by size as you go down the periodic table, so size is a more dominant factor. And size significantly changes as you go down, but not as significant along a row. And so that's why you don't see size along the row. Electronegativity thus overlaps as more potent. Okay. So that's the first thing you might look for, is there an element difference? Then let's say you have this one and this this one, and let's say something like that. Has the same number of carbons, it's still organic, all the elements are the same. So now you're looking for a different kind of difference. And here, the difference you're looking for is resonance. And you're either looking for bonds or usually oxygens. Okay, in this case, the one on the bottom has more oxygens. It's going to cause it to have more resonance in the conjugate base. So this one's going to be the stronger acid. If I wrote it in base form, then it would be the weaker base. Okay? So between the top one and the bottom one's the stronger acid because of resonance. In this case, you don't see an element difference, so you go to resonance. The third thing you might be looking for is an H versus a Cl or F. This is the inductive effect that somebody asked me about earlier. So it's H in an organic compound typically versus a fluorine or a chlorine. That's the inductive effect, and the one with the fluorine or chlorine is going to be stronger. So if I'm comparing these two right here, the top one is a stronger acid. That's it. So you're looking for this is what you're looking for here. The first and the third one are easy to recognize because it's an element difference. Okay? So the first one's an element difference, it's not the third one. And if you don't see an element difference, it's probably the second one. Okay? There could be a couple other scenarios. One other scenario, if you take a look at this here. So don't be fooled. Sometimes I just give you two of these. And all you need to do is look on this table. So if it looks totally random, or maybe I can say this in reverse, look at the question and see if it's any of these. If it is, just compare the Ks. So the one with the larger K is a stronger acid. So just because it's a comparison between two doesn't mean you're using one of these three observations. It could be just, I want you to read a table. Okay, and it's super easy because you're just looking at numbers and you tell me which one's the bigger number. It's a stronger acid. Okay? Or for bases, whichever one's the stronger, bigger Kb is the stronger base. All right. That's acid, base, or neutral. Moving on. There's no questions. All right. No, that was this relative acidity. Let's do the dilute strong acid. How would you recognize this problem? Well, a dilute strong acid would be, you would see a strong acid, so for example, HNO3. And then you would see a concentration that's around 10 to the minus 7, somewhere around there. So for example, 2.0 times 10 to the minus 8. Okay, that's a dilute strong acid. It's somewhere around 10 to the minus 7 concentration. If you saw a concentration that was more like 0.5 molar, this is not this kind of problem. Okay? That's not even close to 10 to the minus 7. So let's kind of do both, just so you can see the difference. If you have a strong acid as a normal concentration, like the one on the right, then that concentration is equal to the H3O plus, only because it's a strong acid. You say pH is negative log of 0.5. Whatever that number is the pH. In the case on the right, because it's a concentration around 10 to the minus 7, then you have a lot of mess to work with. So what I recommend doing is writing the Kw equation. Writing that out. The book solves this a little bit different, but this is the ion product of water equation. Okay, and then what I do, I solve it sort of like it's an ice table, where initially I know the H3O plus concentration is 2.0 times 10 to the minus 8, and this is 0 because of what's given. But I know it shifts to the right, and the reason I can't just take the negative log of that 2.0 times 10 to the minus 8 is because water also contributes a significant amount of H3O+. So in that case, I have this kind of equation. And so Kw is just products over reactants, and there's only products in this case. 2.0 times 10 to the minus 8 plus x times x. And Kw is given on the back of the exam, 1.0 times 10 to the minus 14. This, unfortunately, will be a quadratic. It's unavoidable. You'll have to solve the quadratic. The good news is, there is possible good news in this problem. Okay, because it's a dilute strong acid, what do you expect? So x, well, the pH is going to be the negative log of this number right here. What do you expect the pH to approximately be? Is it close to 1, close to 4, close to 6, close to 7? Around 7. I'd expect it to be no lower than 6.8. And, well, I guess I should do it this way. Somewhere between, greater than 6.8 and definitely less than 7. So usually around 6.9, 6.95, somewhere around there. So if it's a multiple choice problem, I wouldn't even do any calculations. I would just pick the number closest to 7, but it's not above 7. Done. Okay? Yeah? Why do I use Kw? Well, first of all, I wrote the Kw equation. So I have to use Kw. There are other ways to solve this. I'm just showing you my way, which I think makes the most sense. But if for some reason you don't like it, the book has another way of doing this that ends up with the same answer. But since we're used to the rubric of the ice table, I'm just following that pattern, and I'm just telling you, just always write this equation. And this equation does occur predominantly when the concentration of the acid is really low. All right, so that's it with that problem. They're all solved the same way. Okay, let's do a percent ionization. There's two ways that you could see a percent ionization. So first, the equation. You need to know that the percent ionization is going to be the x value. There's two ways you can write it. You can say x over the initial molarity times 100. Well, maybe I'll do it that way. I'll write it like that, and then x, right there, that x. If it's an acid, that's the H3O plus concentration. If it's a base, then that's the hydroxide concentration. And then this, if it's an acid, is the initial concentration of the acid. Or if it's a base, it's the initial concentration of the base. Okay? So it's the percent ionized, or it's the amount of, say for the acid, H3O plus given compared to the amount original. Okay, the x must be from the ice table. So there's two ways you could see this problem. Let me write down the general reaction for an acid. Okay, and let's say you did an ice table with this. And we fill in the blanks. Let's say I give you an initial molarity here, and you ignore water. This is 0 and 0. It would shift towards the 0, like this. You got m minus x, x, and x. And then Ka, because it's equation for an acid, is x squared over m minus x. Okay, so there's two ways that this percent ionization could come about in a question. One way, the most straightforward way, is after you solve for the pH and you're all done with the problem, the next part would say, what's the percent ionization? And you just take the x that you found when you solved the problem, and you divide it by the value m that was given in the problem. That's one way to do it. That's kind of the traditional way to do it. It could also occur backwards, like you have probably saw it in the homework. So we could give you the percent ionization and have you find m. Meaning, I'm giving you the end of the problem and you're going this way. In that case where you're given the percent ionization, you still need to write out the ice table, but we're going to have you find m. You might be wondering, how do I find m? Well, you're going to have two equations and two unknowns. Okay? So basically what I would do is probably solve for x and then stick it in this equation to find out. So if we give you the percent ionization, how do you solve it? I recommend writing out this equation. From the percent ionization, solve for x, write a formula like this, and solve for x in terms of m, and then put it in here. That's how I'd recommend solving. So that would be kind of the reverse problem. Any questions before we go to the next part? Okay. So check out your homework if that sounds a little fuzzy. Okay, let's do polyprotics. And that'll finish off the questions you had this time for chapter 15. Polyprotics, let's just take, somebody asked me a question about this. Let's say you saw this and this together. You would think what? It's polyprotic and they're conjugates, and that means they're a buffer pair. They're a buffer pair. Which one is the acid? The one on the left or the one on the right? The acid's on the left, the base is on the right. You know the acid's on the left because it has more hydrogens. So one way to give you a buffer pair is basically give you conjugates that look kind of funny, but if you see they come from the same root of the phosphate in this example, then you just look, oh, does one have more hydrogens than the other? I guess it's a base pair, acid-base pair. Now, this goes along with it. Ka, what? Ka, there's 1, 2, or 3 is your only choice. Okay, if you don't know, which you sounds like you don't, write these out. So you would write out, I guess I have them written behind me as well, but, oh, well, okay, after there, that's kind of crazy. H2PO4 minus plus H3O plus, and then take the product and write it again as losing a proton. Oh. And you would immediately, hopefully, see the first one is called Ka1, the second one's Ka2, and that's the one that has my acid-base pair in this example. Okay, so Ka2 would be associated with this pair. Ka1 would be associated with this pair, where my finger and pen are. Okay, so that's how you tell which Ka goes with which one. Polyprotics, you'll see in the notes, there's 2 possible ways to solve them, depending on what we give you. If we give you a polyprotic strong acid, what's our only polyprotic strong acid? H2SO4. So that's the only possible one. If that one's given, no ice table is necessary. So you'll see when we solve that one in class, you might want to refresh your memory and look in the notes if you forgot about it. We did not use an ice table. The concentration of the sulfuric acid is equal to the H3O plus concentration. Okay, every other polyprotic is a weak acid, and so thus we must use the ice table. Okay, so you use the ice table in the first step. There's only one additional thing I want to point out before we move on. The Ka2 value, it just happens to turn out this way for your normal polyprotic that we do in our class, is equal to a special concentration. Does anybody know which one it is?
H3O4?
Yeah, it's equal to, in this case, the concentration of the entity that has lost 2 hydrogens. So see how it started with H3PO4, so subtract 2 hydrogens from that. In this case, just HPO4 2 minus, that concentration is equal to the Ka2 value. It just happens to derive out that way. So that's something nice to remember. If you've looked at the practice exams, you'll see that that's a common multiple choice question, where you could calculate that and waste a lot of time, or if you just remember this idea, it's a quick, you can get this in 10 seconds. Oh, is this the one that's lost the 2 protons that I'm asking about? If so, it's just the Ka2 value. Okay? So this is a good thing to remember. All right, I'm going to move on from polyprotics. Yes? Why did that sound weird or confusing? Oh, for sulfuric acid, is the concentration of sulfuric acid is equal, the concentration of H3O plus is equal to the sulfuric acid concentration. You don't need to multiply by 2 because only the first proton comes off easily. The second one does, so you probably think of stoichiometry a little bit. But now that we know that that's a strong acid, that second proton is not going to come off very easily. And so we consider them totally separate. So we're only taking off 1 to give us that H3O plus concentration.